We'll be talking a little bit about everything. We'll address the technology. We'll discuss different myths and misconceptions about lithium-ion batteries, address some differences between lithium-ion batteries and other chemistries. Talk about safety, talk about our E13 lithium-ion battery standard, which is under the review right now. That's the first systematic review, so it's not that new. Uh, we'll touch on some practical considerations, such as load dump and how to deal with the transient voltages, and also discuss things that are outside the scope of the standard, like all these toys, and other portable devices that are powered by lithium-ion batteries. So first, what is the lithium-ion battery? And Jason already discussed a little bit about that, so I try to be short here. Uh, First, this is not how the lithium-ion battery look, but it kind of shows how it works. So it is a rechargeable battery that uses lithium ions to store and transfer energy, and that's the true for all the lithium-ion battery chemistries. So what we have here, we have the cathode, the positive electrode, and the anode. And the cathode is typically some lithium oxide or lithium salt. And in majority of the batteries used on boats, that would be the cathode material will be lithium iron phosphate, which we'll be talking about. And the anode is typically graphite. Between the anode and the cathode, you have the electrolyte, and that's where all the positive lithium ion moves. So I said that's not how the lithium ion cell look inside. So that's pretty much how it looks inside. The cell that you can see on the right, it's part of my destructive testing that conveniently shows all the layers of the internal components of the cell. So you can see the copper current collector, and basically what it is like a tightly wrapped layers of the cathode material, anode material, plastic separator, and the copper current collector. So that kind of shows how important is quality of the cell construction, because everything is really thin and really close together, right? And talking about the chemistries, and we'll address that in a few slides later. But basically, these are the major chemistries. And when we talk chemistry, we talk about the cathode chemistry of lithium-ion batteries. Some of them are used on boats, and you can see the orange ones here. That's LFP, lithium iron phosphate. That's like 99% of the batteries that you will find as the batteries installed on boats. The NMC batteries are typically used in high voltage electric propulsion applications that use the automotive systems that were marinized. And other systems are used outside the marine world. For example, your lithium cobalt oxide batteries would be used on portable devices like cell phones, laptops, everywhere where the weight is a factor and the high energy density is important. NMC, that's one of the, for example, I think that's the Torpedo battery, the high voltage deep blue battery. That's I think they use the marinized BMW systems. So these type of batteries you can see in the high voltage electric propulsion systems on boats, but they're not commonly used as a replacement for the lead acid batteries. And finally, we have our lithium iron phosphate batteries, which I'll repeat that probably a few times today. Lithium iron phosphate is lithium ion battery. That's one of the myths that we'll discuss in the future, but that's one of the most commonly used chemistries on boats with its own unique characteristics. And talking about these unique characteristics, You can let's start from discussing the specific energy and what makes lithium-ion batteries a little bit better than the traditional lead-acid chemistry is that specific energy. So that's energy per unit mass. So basically, if you take your 1 pound or 1 kilogram for my metric friends of the battery, how much energy that 1 pound can or 1 kilogram can provide. And in that case, we'll describe that in watt hours per kilogram. And we can see that a lithium iron phosphate battery can have approximately 3 times more of the usable energy than your traditional lead acid batteries. And of course, that will vary because there are different lead acid batteries and different lithium iron phosphate batteries. But we can see the difference here. Also, when we talked briefly about lithium cobalt oxide batteries, those that are used in your cell phones, these have even higher energy density. So they are used when the low weight is an important factor. And typically, we describe the capacity of the lithium-ion battery in watt hours, not like we were used to in amp hours. All because these different chemistries of lithium-ion batteries have a little bit different voltages. So watt hours provide more uniform reference. But if you are used to amp hours, you can see that you can easily convert that, go from amp hours to watt hours and from watt hours to amp hours using your power equation. So we're not spend too much time doing math here, but I just want to point it out that it's fairly easy to convert from one to the other. And let's talk about why chemistry matters. So let's talk about the thermal stability. And when I talk about thermal stability, it's basically the ability of the cathode material, because that's the important part here. Ability of that material to resist decomposition when there is a high temperature applied to that material. So we probably have seen or heard about cases when the lithium ion battery will burn even if it's underwater, when the external atmospheric oxygen is not available. So when that oxygen that's needed for the fire comes from, it comes from the decomposition of the cathode material. Let's jump quickly to the next slide. So for example, if we are talking about the separator between the cathode and anode before. So if that separator fails, we'll have the short circuit between the anode and the cathode. And that short circuit will create the elevated temperature. If that temperature is high enough to decompose the cathode material, that will release the oxygen to the reaction, even if there is no atmospheric oxygen available. And that shows you what that thermal stability is, what that oxygen release temperature is for the different chemistries of lithium-ion batteries. So as we can see, the LFP, lithium iron phosphate, it got pretty high thermal stability. When other chemistries, like for example here, lithium cobalt oxide, it's only 150 degrees Celsius, approximately. So that sometimes some people discuss that LFP is safer than lithium cobalt oxide. If it's safer or not, that's up to the discussion, because there are a lot of different factors than just the oxygen release temperature that affect safety. But so that's the thermal runaway mechanism. That's how it works, and that's why we call it like a self-propagating exothermic reaction, because you are able to get the oxygen and fuel that oxygen to the fire from that chemical reaction when the cathode material is decomposed. And there are multiple factors that can lead to that. So So first, that initial temperature raise is usually from that short circuit that is inside the cell. Uh, so we can have that from either overcharging or over discharging or some mechanical damage, anything that will disrupt that separator between the anode and the cathode. And I've done some backyard testing on that we'll discuss later. So we could see some elevated temperature. If they were high enough to create thermal runaway, we'll discuss that in a few minutes. Life cycle. It's another aspect of the lithium-ion batteries that make them well, better than traditional lead-acid batteries. Of course, it all depends how the batteries are used or how they're abused. Yes, usually batteries don't die; they're just brutally murdered. But it's much difficult to murder the LFP battery. It takes many more cycles than the lead-acid battery. On the other side, LFP battery will also have the BMS, that is a protective mechanism. So let's compare quickly lithium-ion batteries and lead-acid batteries. We discussed higher specific energy in lithium-ion batteries. You can have significantly more cycles of charging and discharging. When it comes to lithium-ion batteries, there is no routine electrolyte leakage or venting of the hydrogen like you have in your lead-acid batteries. When you have venting in lithium-ion batteries, that means something went wrong, and that's the situation we're trying to avoid. The charging time, because of the low internal resistance of the batteries, it's much shorter in lithium-ion batteries. We'll discuss the voltage curve in the second, but basically the lithium-ion batteries have much flatter discharge curve. Because of the Puker effect, they're more suitable for higher loads, and also we'll talk about that in a second. And they're protected by the BMS. That's like a heart of the lithium-ion battery system. Okay, so we can see our discharge curve here, and that basically represents the relationship between the voltage and the state of charge. So for your traditional lead-acid battery, you could determine what's the state of charge based on the voltage. You can't do that in lithium-ion batteries because the voltage curve will be much flatter. And when you see the drop in voltage, that means the battery is pretty much done, the lithium-ion battery. But that also makes it more suitable for many applications when more steady voltage is needed. And I was thinking maybe if we should go to the Puker effect because maybe not everybody is interested in great German scientist William Pukert, but that's the important thing is because that's why we have all that electrical revolution, we could say. We can say much higher loads, like electric propulsion on boats, large inverters, simply because lithium-ion batteries are much more suitable for higher loads because of the traditional the Puker loads describes how the battery capacity will decrease when you apply big load. So when the discharge rate increases. And in case of the lead-acid batteries, when you see that these red lines here, the higher the load is, the less of the usable energy you can take from the battery. The lithium-ion batteries, they perform much better for these higher loads. So they're much better fit for application like large electric motors or large inverters. Okay, let's talk about some myths, mythology, and misconceptions in lithium-ion batteries. And let's jump to the first one. That will be a drop-in battery, drop-in replacement battery. So uh, when we talk about drop-in batteries, we typically refer to the batteries that are of the same size or or and can like your typical lead acid battery cells. So basically they represent like group 24, group 27, group 31, and they look exactly the same from the outside as your typical lead acid batteries. And you can even see that the like a screenshot from one of the manufacturers that the drop-in lithium battery are designed to seamlessly replace the lead acid battery without the need for modification to the existing system. Is that the true? Not necessarily. That's why I don't like the term the drop-in replacement battery because it's in many cases misleading because there are several factors that you have to consider when replacing your lead acid battery with lithium ion battery, lithium iron phosphate, many more things to consider than just size. So the charging sources and charging profile, they must be suitable for the voltages of these batteries. Uh, when we'll be talking about overcurrent protection in a few minutes, and AIC rating of the fuses and switches. It might be different than what was necessary for the lead acid battery. And finally, we have to discuss the BMS shutdown, something that's not the problem for your lead acid applications. Here, I mean, the BMS shutdown should be like a last line of the defense and shouldn't really happen in well-designed system. But still, we have to think what happens if and how to deal with the shutdown so we won't damage the equipment on the boat. So there are several factors to consider when replacing lead acid battery or lithium-ion battery. So drop in without modification of the system, not exactly true. The next myth, lithium iron phosphates are not lithium ion batteries. And I hear that again and again, multiple times from many angry online experts on different forums and social media that these are two different things. When in fact, like we discussed before, lithium iron phosphate are just one of the chemistries of lithium ion batteries. It's one of the types of lithium ion battery. Lithium iron phosphate is just a cathode material of the specific type of lithium ion battery. It has different properties than other types of lithium ion batteries? Yes, they all do. They are all different. So, yes, our standard E13 lithium ion batteries apply to all types of lithium ion batteries, including lithium iron phosphate. I'm sure I'll have to discuss that again and again, but I just re-emphasize that these are lithium-ion batteries. And talking about the standard, that's what we have here. We started that with the Tech Info report, and 3 years ago, we published the standard the first time. Right now, the standard is open for the systematic review, and we'll be publishing the first updated version this year. The draft is almost ready. It's out for the consensus ballot and public review. So the committee will address all the changes, but I can give you a little bit of sneak peek into the changes that are upcoming in this publication. So what's in the scope of the standard? It's basically it's an installation standard. So it talks about selection of the batteries, installation, system design, It doesn't address the construction of the battery, but it talks about the testing standards for the lithium-ion batteries. And standard applies to all battery systems over 600 watt hours. So we can easily convert that to the amp hours for those of us who think in amp hours. So it will be around 50. But I think that will change in the next publication to 500 watt hours. Very little change. Okay. So before we jump to the requirements of the standard, what are the typical problems and what the main causes of failures in lithium-ion batteries? So it can be high voltage or low voltage, and same high current, low current, and that's why we have the BMS to be our last line of the defense. Again, the well-designed system. We shouldn't have like a high voltage situation because we'll have the communication between the battery and the charging source. So that will manage the charging current. The high temperature and low temperature, again, that would be battery will be protected by the BMS because there are specific limits for the high and low temperature. If they're exceeded, the BMS will shut down the battery. The cell failure, we all seen how the cell is built, so the cell quality is very important. That's why the standard requires certain testing to be done and to comply. External damage can result in the battery failure. So if somebody puts a nail through the battery, which we'll be discussing in a few slides, proper installation, proper place for installation is important, so the battery is not exposed to that damage. And the water ingress is one of the most common problems in lithium-ion batteries. So if they're installed in places that are exposed to the water, splash, rain, they should have adequate level of water ingress protection. And there are two main terms that the whole standard is like evolving around. It's a safe operating envelope, and we'll be changing that to the safe operating limits. But basically that concept remains the same. That it's that set of limits that's specified by the battery manufacturer. It's like a low voltage limits and high voltage limits, low temperature limits, high temperature limits, current limits, within which the battery must be operated. So the system should be designed this way, so the battery is never exposed to these limits, and the BMS won't have to shut down the battery either to the charging source or to the load. But in the worst case scenario, you always have the battery management system that's designed to protect the battery if that hazardous condition exists.